Today's webinar is about the Hall characterization system HCS from Linzais. So let me start with some organizational information. All participants are muted, so you can't talk to me. If you have any questions, please feel free to type them in the chat, and I will answer your questions at the end of this webinar. You can also use the chat in case of any problems or comments you have. This webinar will be recorded, and you will get an email link with this recording after the webinar, probably beginning of next week. Okay, so I'm your today's presenter. My name is Hans Marx. I do application support and sales for Linzais since more than or almost 13 years. My scientific background is that I studied chemistry at the University of Aachen in Germany. My spoken languages are German, French, and English. So if you do not feel comfortable with English, you may type questions as well in German or in French. So I will start with an introduction first to the company and then to the Hall effect, explaining what this is. Show you an overview over the Hall measurement instruments from Linzais called HCS1 and HCS10. I will show you the sample holders, present some system add-ons and options to you, present the software, and I will finish with some application examples. And after the application examples, I will answer your questions which you typed in the chat. So the company Linzais was founded almost 70 years ago by Dr. Maximilian Linzais, whom you can see here on the left-hand picture, and was founded in the city of Velp in Germany. All the manufacturing up to this day is situated in Velp in Germany, and we have own sales and service locations in the USA and China and India, and we are represented by more than 65 dealers worldwide. After the foundation of the company by Maximilian Linzais, it was his son Klaus Linzais, and later on his two sons, Florian and Vincent Linzais, who took over the company. And so we are now in the third generation. Our business area is the manufacturing of measurement instruments for thermal analysis, for the measurement of thermal conductivity, and for the characterization of thermoelectric materials. Besides this manufacturing of instruments, we have application labs in all these countries and in Southern Korea as well to do service measurements. So we have a quite broad product range. We manufacture differential scanning calorimeters, DSC, which are used to monitor phase transitions and chemical reactions. We manufacture thermal balances to monitor chemical reactions. Simultaneous thermal analyzers, which are a combination of a thermal balance and a DSC, so that you can perform these two measurements in one instrument in one run. We manufacture thermomechanical analyzers and dilatometers for dimensional changes of samples. We have a very broad range of analyzers for thermal conductivity and thermal diffusivity. We have analyzers to characterize thermoelectric materials and to measure physical and thermophysical properties of thin films. Beside this, there are a lot of optional equipments like evolved gas analyzers, which can be coupled to the thermal analyzers. And we do a lot of customization, so we build high pressure instruments, instruments which can work under corrosive atmosphere, under pure hydrogen atmosphere, instruments which can be installed in glove boxes and hot cells and so on. So whenever you need an instrument, a particular instrument, we may build it for you tailor-made. But today's topic is the Hall effect analysis. So our Hall characterization systems, HCS, can measure the Hall coefficient and the electrical resistivity and conductivity. From these two parameters, the Hall mobility, the charge carrier concentration can be calculated. The type of the charge carriers may be measured, the sheet resistance, and also the magnetoresistance. And all these measurements can be performed on thin films and also on bulk materials. The used measurement method is a Van der Pau method. I will show you later how this is done. And there are a couple of options like the gated Hall bar measurement, the Seebeck coefficient measurement, and an illumination accessory. So first of all, what is the Hall effect? The Hall effect appears when a magnetic field is applied perpendicular to a current flowing through a conductor. And it describes the phenomenon that a voltage is created which is perpendicular to both, to the direction of the current flow and of the magnetic field. This is, this is shown in this scheme. You have a sample, you have a current flowing through the sample, you have a magnetic field perpendicular to the sample and the current. And in this case, you can measure a voltage perpendicular to both the magnetic field and the current. And this voltage is called the Hall voltage. And the Hall voltage equals the Hall constant. It's a material-dependent constant multiplied with the current, with the magnetic field strength, and divided by the thickness of the sample. So in order to measure big voltages, even for small Hall constants, you should use quite thin samples. The sign of the Hall voltage indicates the type of the charge carrier. It may be electrons or holes, so positive charges. And the charge carrier concentration can be calculated by this formula. The charge carrier concentration equals 1 divided by the Hall constant and the elementary charge. The Hall mobility equals the Hall constant divided by the electrical resistivity. And both parameters are measured with the HCS instruments. So, we use the so-called Van der Pau method to measure the Hall constant and the electric resistivity. This is a kind of a 4-point measurement method and allows to measure the sheet resistance and the Hall coefficient. The advantage of this method is that almost all sample shapes can be measured. There are just a couple of requirements. For example, the sample thickness must be homogeneous and it must be small in relation to the distance between the contacts. And the 4 contacts must be on the very edge of the sample and they must be small in relation to the area of the sample. This is shown in this scheme. So it's an irregular shaped sample with 4 contacts on the very edge of the sample. They are very small compared to the surface of the sample. And their distance is big compared to the thickness of the sample. And the measurement principle is you apply a current between 2 contacts, in this case between A and B, and you measure the voltage drop at the other 2 contacts, C and D. And you do this in one direction. So in this case, the current is applied in the vertical direction. In a second measurement, you apply the current between B and C and measure the voltage drop between A and D. And if you have done such measurements, you can calculate the resistivity by this Van der Pau equation. So the electric resistivity can be calculated. You have to know the thickness of the sample and the resistances measured for a voltage AB, a current AB, and a voltage CD, and a current applied at BC, and a voltage DA. In order to calculate the Hall constant, you use this formula. So again, you have to know the thickness of the sample, you have to know the magnetic field strength, and you have to measure resistances. And the resistances have to be measured at two different field strengths, usually at a field B1 and the second one at a zero magnetic field, B0. So I want to present two HCS instruments, the HCS1 and the HCS10. The HCS1 is a permanent magnet version, while the HCS10 uses an electromagnet. This is the main difference between these two instruments. The magnetic field strength is a little bit lower for HCS1. It's 0.7 Tesla. And for the electromagnet version, it's 1 Tesla. Both instruments are available with different temperature options, with a liquid nitrogen cooling for low temperatures, and they may be heated up to 600 degrees centigrade. And this holds for both types of instruments. The permanent magnet version covers most applications, and the electromagnet version is used for more challenging applications. If we compare the technical specification, you see that resistivity and charge carrier concentration measurement ranges are the same for both instruments, but you can measure lower mobilities with the electromagnet version. So let's have a look first on the permanent magnet version, so the HCS1. You have a measurement chamber with a sample holder board and the sample here in the middle. And you have two permanent magnets, one on the left and one on the right-hand side. On the right-hand side, it's a negative magnetic field. On the left-hand side, it's a positive magnetic field. So in this shown position, you may measure the properties at zero magnetic field, and then you push by these handles the magnet over the sample, and you can measure the properties at negative field. After having done this, you push the other magnet above the sample, and you perform the measurement at positive field. So this is a manual version. You slide the magnets from left to right, but it's much more convenient, mainly if you have to perform measurement at different temperatures, to do this with an automatic field change. So in this case, there is a motor which drives the magnets from positive to zero to negative field. In both permanent magnet versions, in the manual and in the automated one, you can place different sample holders. We'll see them later on. There are different temperature options, from liquid nitrogen cooling, either by quench cooling down to -196 degrees centigrade, or by controlled cooling from -150 to high temperature. And there are high temperature options available up to 600 degrees. The measurement chamber is vacuum tight, and there are gas in and outlets so that you can perform measurements under a defined gas atmosphere. The inlet for the liquid nitrogen is here on top to do the cooling of the stage. And there are options available, which I already mentioned, the Seebeck option, the elimination option, and the gated Hall bar option. The electromagnet version looks like this. You have the same type of sample chamber, measurement chamber and sample holder stage with inlets for gas and for liquid nitrogen. But in this case, you have an electromagnet, and you can use a direct current power supply to do a shift of the magnetic field from -1 Tesla up to +1 Tesla. Permanent magnet version, you have just 3 fields: negative, -0.7 Tesla, 0, and +0.7 Tesla. In the electromagnet version, HCS10, you can do a sweep from -1 to +1 Tesla. The other options like sample holder stages, temperature options, gas inlets, and so on are all the same like in the manual version HCS1. With just one further possibility, due to the electromagnets, it's to use an alternating power supply, so an AC power supply. So you can shift the magnetic field in the AC manner. This has some advantages, which I will explain now. In the ideal case, when you have no magnetic field, you should measure no Hall voltage. But in the reality, sometimes there is an offset voltage, and this offset voltage contains contribution of the so-called misalignment voltage and the thermoelectric voltage. So in direct current magnetic fields or in the permanent magnet HCS1, the misalignment voltage and the thermoelectric voltage can be removed by inversion of the current and inversion of the magnetic field. But materials with low mobilities, it may happen that the Hall voltage is much smaller than the offset voltages. And in these cases, the DC method comes to its limit, and you have to use the AC magnetic field. The AC magnetic field is shown here, the equation. And the misalignment and thermoelectric voltages, so the offset voltages, do not depend on the magnetic field and can be separated. And this is done by separating the AC from the DC signal with a lock-in amplifier. So the electronics of the instruments consist of an optimized direct current electronics, which is built in-house by Linzais, and it allows to perform measurements for highly conducting metals to highly resistive semiconductors. It allows to perform fast measurement cycles and has a very broad range for input currents. Using the AC method, we use a lock-in amplifier in the combination with the HCS10 electromagnet. And there is a third part of electronics. This time again, it's an in-house development to program heating and cooling cycles, to do gas dosing, and to do the polarity change of the permanent magnets and of the current. So you need the instrument, you need sample holders. There are different sample holders available for different sample sizes, which you can see here in this picture. So there are these green sample holders for measurements up to 200 degrees centigrade. And you can do this depending on the sample holder for samples from 5 by 5 up to 50 by 50 millimeter square. If you perform measurements at high temperatures, you have to use such a ceramic board, which resists up to the maximum temperature of the device, which is dedicated to smaller samples, up to 10 by 10 millimeter. The sample holders have these 4 pins, which are put on the sample, on the edges of the sample, and the sample is heated by an integrated heater here in this board. Once you placed your sample on this heater, you plug this board inside this blue box, and then you slide this blue box here inside the machine. And you can see here on this picture the gas in and out lets, for example, for uses of inert atmosphere. I talked about, or I said that there was an option to measure the Seebeck coefficient available. So first of all, what is the Seebeck effect? The Seebeck effect describes the phenomenon that a temperature difference creates an electrical potential. So if you have a thermoelectric material, you heat it on one side and you cool it on the other one, then you have a temperature difference between the hot and the cold side, and you can measure a voltage, the so-called thermoelectric voltage. The Seebeck coefficient is the voltage, the thermoelectric voltage, divided by the temperature difference. Such measurements may also be performed with a HCS instrument. You need this option and an optional sample holder board. This holder board can be used at low temperature, and it can be heated up to 200 degrees centigrade. And it has an integrated heater to create a temperature gradient on the sample. There are 2 thermocouples type K on both ends of the sample to measure the temperature difference from the hot and the cold side, and to measure the thermoelectric voltage. In this case, the sample geometry has to be bar-shaped, and all the measurement is done fully automatically, and the evaluation is done by the so-called, or the measurement is done by the so-called slope method. The slope method is done like this. So you have a certain mean temperature of the sample, and you apply different temperature gradients, different temperature differences between hot and cold side. So for example, your sample, your mean temperature is at 100 degrees centigrade, and then you apply a temperature difference, in this case of 3 up to 11 degrees. And if you do a plot of this thermoelectric voltage over the temperature difference, you get a straight line. And the slope of this straight line is the Seebeck coefficient. And you may perform measurements of the Seebeck coefficient at different temperatures and get a plot, for example, like this. And every dot on this plot was obtained using different temperature gradients, different temperature differences at every mean temperature of the sample. There's a further option is a so-called illumination option. So you can irradiate the sample by blue, green, or red light. You can vary the light intensity and do measurements of the electric resistivity and the Hall coefficient while illuminating the sample. This may be quite interesting for materials used for photovoltaics. With the instrument comes dedicated software. This software has a current status bar showing the actual temperature, the nominal temperature, the polarity of the magnet, and so on. There was a function to find the maximum current you should use. You can do this automatically or use the manual measurement setting. You can set up a heating profile. So in this case, 30, 35, 45 degrees, and so on, and define a heating rate to go to every dedicated temperature. The more convenient way to do a temperature profile is using the profile visit. So you can set the minimum and the maximum temperature you want to use. You set a step width, in this case 10 degrees, and a heating rate, in this case 10 Kelvin per minute. And then you can set up such a measurement profile in a couple of seconds. Sorry. Before starting a measurement, you should do a connection test. So you should check that the contacts between sample and the spring pins is a good electrical connection. And for doing this, you apply different currents and measure the voltages between the four contacts. And this should give 4 straight lines. If you plot the resistance over the measurement current, you should get 4 horizontal lines. So if this connection test looks like this, you can perform your measurement. If it does not look like it should, you have to prepare the contacts to the instrument in a certain way. In the easiest case, it can be done by using a conducting paste. Otherwise, you have to solder the contacts on the sample or to sputter contacts between the pins and the sample. At the end of the measurement, you get a report which shows the measurement settings, which shows the Hall voltage or the Hall voltage over the magnetic flux density. So this is done at 2 different geometries, and the intersection should be at 0 field, like it's the case in this example. You find the measurement raw data, and you find the results. So you can read the sheet resistance, the electric conductivity, the resistivity, the sheet charge carrier concentration, and the bulk charge carrier concentration, the Hall coefficient, the magnetoresistance, and so on. This report can be exported as an Excel file or as a PDF file. And if you perform measurements at different temperature, you can plot the Hall coefficient depending on temperature, and you can plot the sheet resistance depending on temperature as well. So let's have a look on a couple of application examples. The first measurement shown here on the left was done with the HCS 10, so with an electromagnet. It was a sample of bismuth antimonide was analyzed. It was a thin film of 150 nanometer thickness, which was thermally evaporated. And the measurement has been done from room temperature up to 170 degrees centigrade. And you can find here in green the Hall coefficient, in blue the electric resistivity, and in the red color the mobility, which is calculated from the Hall coefficient and the resistivity. The second example is a measurement done with a permanent magnet version. A thin film sample of 185 nanometer thickness, which was obtained by sputter deposition, was analyzed, and the material was indium tin oxide. Indium tin oxide is also used to check the performance of the instrument. In this case, measurement was done from room temperature to 150 degrees centigrade, and again you find the Hall coefficient in green, the electric resistivity in blue, and the mobility, which is calculated from resistivity and Hall coefficient, is shown in red. The last example I want to show is a measurement of the Seebeck effect using the Seebeck option on a HCS. In this case, a Constantan sample was analyzed. Constantan is also used to check the performance of the instrument. And this Constantan sample was investigated in a range of minus 130 to plus 180 degrees centigrade. And you find the Seebeck coefficient depending on temperature. And every dot, which you can see here on this graph, was obtained by using the slope method, so applying different temperature gradients and measuring the thermal voltage at different gradients. And the slope, in this case, a negative slope of 36 microvolt per Kelvin, is the Seebeck coefficient. It's a negative one in this case. So I thank you for your kind attention. If you have any questions, please type them in the chat. I will answer them right now. This was the last webinar for this year. We'll have further webinars the next year. You can find announcement of the webinars on our website and on our Facebook and LinkedIn channels. If you have any questions later on, you can contact us by phone, by email. You will find useful information and brochures on our website. Don't be shy, just contact us. And don't forget, we have a test laboratory, not only in Germany, but also abroad. So if there is any need for service measurements, we can do this as well.